Okay, today I'm going to do several problems that follow up from the week 5 material, but they're essentially applications of the dot product, the cross product, and the projection formula. And so if I recall correctly, that chapter was applications of vectors, or vector products it says, right? So we really should do some applications of those. So these are problems that I did in my tutorial sessions, but I feel that everyone should do these. So the first one says, find the scalar equation of the plane that's parallel to the vectors A and B given there and contains the point 1, 2, 3. Okay, so the first thing I want to do is sketch a diagram here. Now it won't leave a lot of space for the mathematical workings, but it's pretty important. Okay, here I've got a plane, right? And then suppose I have vector A parallel to that plane, but let's suppose it's just on it in this diagram. Okay, and then we have vector B off in this direction, also parallel to the plane, but we can bring our plane up to the vector so that we can consider it to be on it. Okay, and then let's draw a vector that is perpendicular to both A and B, and therefore perpendicular to the plane. And let's call that N for normal vector, but we can calculate it via the cross product. Okay, now over somewhere, say here, we might have the point 1, 2, 3. And then also on the plane, let's choose an arbitrary point x, y, z and call that uppercase X. You can see the diagram's a little small now. And now I want to form the vector px. Now remember, since P and uppercase X are both points on the plane, this vector Px is also parallel to the plane. So, and let's give it the name lowercase r equal to Px. Okay, so now we have sketched enough there to be able to complete this problem. So let's first work out what our vector Px is. So the vector r, which is Px, now there's a formula for this, right? It's x minus p as vectors. And so that's x, y, z minus the point. So 1, 2, 3, and let's simplify this. So now we have x minus 1, y minus 2, and z minus 3 is our vector r that is parallel to the plane, and it's actually on the plane because we have a point taken on the plane. Alright, now the cross product of A and B is perpendicular to both the vectors A and B. And so let's calculate this cross product. Remember, we put I, J, and K, and then we write A as a row there in the second row. So 2, 0, 1, and then B as a row in the third row because it comes second there. And now I need to calculate this determinant. So remember how we do this. Expanding across the top row, we have this is equal to a 2 by 2 determinant times I hat, and then minus a 2 by 2 determinant times j hat, and then plus a 2 by 2 determinant times k hat. Okay, and the way that we work out these three 2 by 2 determinants is we cross out the row and the column that I is in and look at what remains and put that next to I. So that's 0, 1, minus 1, 4. And then we do the same thing with j. Now I'll point out again, these signs alternate because when we expand a determinant, we take across the top row and we have these signs across the top row. But you could expand the determinant along a column. And so we have this checker pattern here, which tells you the signs that go in front when you expand across any given row or column. Okay, since we're doing the top row, we're going across here, and these are the signs that we take in front of these. Okay, so for the determinant that goes next to j hat, we cross out the column and the row that j is in, and so we have 2, 1, 3, 4. Okay, next, the column that k is in gets crossed out, row that k is in gets crossed out, and we have 2, 0, 3, minus 1. Okay, now the determinant of a 2 by 2, so again this will be a side note, so det A, B, C, D is equal to AD minus BC, and you can think of that as the product of the diagonal elements subtract the product of the off-diagonal elements in a 2 by 2. So that's a C there. I don't think you can see that. There we go, BC. Okay, so back to this. 0 times 4 is 0, but I'll put a bracket around this because I don't want to forget the I hat. So we've got 0, and then minus, the product of minus 1 and 1 is minus 1. Okay, next, minus brackets j hat, and then plus brackets k hat. So this determinant is 2 times 4 is 8, minus 3. Okay, now down here next to the k hat, we have minus 2, minus 0. Okay, now I want to simplify this. So minus minus 1 is plus 1, so this will be I. 8 minus 3 is 5, but we have minus, so minus 5 j hat. And then minus 2 minus 0 is minus 2, so minus 2 k hat. And now I've got this in terms of the I, j, and k vectors, but since the problem has column vectors, I'm going to go back to column vectors and express this as the vector 1, minus 5, minus 2. Okay, now this is my normal vector that's perpendicular to that plane. Okay, so now we have all the pieces we need. We just have one last fact before we can write the equation of the plane as a scalar equation. It's just the fact that the vector r, this vector here, label r there, is perpendicular to the normal vector n. Right, and remember there's a product we can associate with this. Right, the dot product equals 0. So n dot r is 0, the scalar 0. Okay, now let's use that with what we have here. So this says that the vector 1 minus 5 minus 2 dot r, which is this one, x minus 1, y minus 2, z minus 3 is equal to 0. Now let's expand that dot product. So 1 times x minus 1 plus minus 5 times y minus 2 plus minus 2 times z minus 3 equals 0. Okay, now if I expand this, we have x minus 1 minus 5y plus 10 minus 2z plus 6 is 0. So there's our scalar equation, but it does need a little bit of tidying up. So to tidy this up, let's collect the like terms, and the only like terms are the single numbers. So 10 and 6 is 16, minus 1 gives 15, but let's take that to the right hand side. So it will be equals minus 15. So we'll have then x minus 5y minus 2z equals minus 15. Alright, so there is the required scalar equation of the plane that we're after. Okay, now let's just check that it does contain the point 1, 2, 3. So x is 1 minus 5 times 2 minus 2 times 3 is equal to 1 minus 10 minus 6. 1 minus 16 is minus 15. So yes, it does. And there's several other points that we could find that are on that plane as well. Like, for example, the point 0, 3, 0 is also on the plane, right? Among many others. There are infinitely many points on this plane, but it's not the entire collection of three-dimensional vectors, of course. Alright, so the next problem I'm going to look at in relation to the week 5 material is the question of deriving again the projection formula, because I feel like many people are still struggling with this even after watching one of my lectures or Lauren's lectures. So let's do it again. Okay, so I'll sketch a vector A, and then I'll sketch a vector, say B. Alright, I'm going to fill in an angle theta between them, and then I'm going to, I think I've got a red pen here, hang on. I'm going to, in red pen, find a vector that has the direction of A, and another vector, say Q. So let's call this one Q, and this little one down here, let's call this P. And then these are perpendicular to, so Q is perpendicular to A, P is parallel to A, and I want it so that the vector B is equal to P plus Q. So I'm pretty sure you can believe that P plus Q gives B, and we've sketched it so that Q is perpendicular to A, and P has the same direction as A. So this is what we want, and it's pretty useful. And I'll show you an application of its use after this. Okay, so what we want to do first is find another way to represent P. Alright, but we'll say we seek vector P such that this is satisfied. Alright, so let's now rewrite what P is. So P is some magnitude of a vector multiplied by the unit vector in the direction of A, which we call A hat. Right, so putting a hat on this vector says this vector here, A hat, has norm 1. And remember that A hat is defined as 1 over the norm of A times the vector A. Okay, now to make this statement true, this vector here has to be P, so this is the norm of P times A hat, okay, which is this right here. So you see it has the direction of A, but the magnitude of it is the magnitude of P, obviously, right? Okay, so good. Now that we've got that, let's fill in a few more details about this, because we've written in an angle here, and I can relate that to the magnitude of B using the cosine. So in other words, I can do a little calculation here. So cos of theta is adjacent over hypotenuse. So the adjacent side there is the norm of P, and the hypotenuse is the norm of B. And so next we want to rearrange this equation so that we express this in terms of the magnitude of P. So the magnitude of P, just by multiplying both sides by the magnitude of B there. So this is norm of B cos theta. Okay, so next I want to substitute that in here. So we've got the norm of B cos theta times A hat, the unit vector in the direction of A. And again, unit vector means that it has norm or magnitude equal to 1. Okay, so now we've got another formula to replace cos theta, because remember, this relates to the dot product with the following formula. So we just have A dot B is equal to the norm of A times the norm of B cos theta. So I can take this and rearrange solving for cos theta, and it goes like this. Cos theta is A dot B over the norm of A times the norm of B, and now we can sub that in there. So let's do that. So the norm of B multiplied by A dot B, remember that's a scalar, over the norm of A times the norm of B, and then we still have A hat over here. Alright, so I'm going to, while we're at it, because I've collected some facts over here, I'm going to put dot points next to each fact that I've used, but this is a rearrangement of that, so I won't put a dot point there, and a dot point here, because that's a fact, and then this is a rearrangement of that fact. So far there are 3 facts that we've used. Okay, so let's simplify this, because we can cancel the norm of B there in our fraction. So we have A dot B over the norm of A, and then times A hat. Okay, and so now let's use our formula up here for A hat, which is 1 on the norm of A times A. So we've got A dot B over the norm of A times 1 on the norm of A times the vector A. Okay, now we can move this over to be with this one, and on the denominator we will have the norm of A squared. So we've got A dot B over the norm of A squared times the vector A. And this is the P that we've worked out. But we've chosen a special name for this. This is the projection of B onto A, because it's like you have a light shining on B in a direction perpendicular to A, and you're looking at the shadow that it casts. Much like a sundial, you see I've got a light here casting a shadow, right? So if I go right underneath that light, which is hard to do here because my light's pointing at an angle, I would get a zero shadow, right? And so if I angle that a bit, I do get a bit of a shadow projecting onto the vector A here. So it's like this, but I think this diagram is a good enough analogy for what we're seeking here. It's as if you're taking the components of B not in an x and y direction, but in an A and perpendicular to A direction. So it's a different kind of components, if you will. Okay, so next I want to show you an application of this formula. And I've maybe not worded question that I have in mind in the best way, but I'll try to explain what I mean. A block of mass 2 kilograms sits on a frictionless surface. So I want to neglect friction here. Incline 30 degrees to the horizontal. Determine the magnitude of the force, so basically in this direction, opposing this force down here. Determine the magnitude of the force required to keep the block in equilibrium. So it's like if you were anchored here, down here, and you had to apply a force to keep this block where it is. Okay? So, what I want to do first is find a vector in xy components that has the same direction as the slope, either this way or this way, doesn't matter which. So to do that, because we've got 30 degrees there, let's just sketch this very useful triangle to remember. It has 30 degrees down here, 60 degrees here, side length 1. On the side, and side length 3 there, and side length 2 there. Okay, so if I take my vector to go this way, then I can say that, let's just call it B, or actually no, let's call it A, because I want to project. So A equals the vector, let's see, I go root 3 in the x direction, so root 3, and then 1 in the y direction. Okay, now this vector is parallel to the inclined surface. Okay, so now that we have a vector parallel, let's just pull this diagram out. So this is the force here due to gravity, and so that's mass times gravity. So we've got a mass of 2 kilograms, and so this is the magnitude of the force, which would be 2g, or 2 times 9.8 meters per second squared. But let's just instead, to keep the math simple, let's call that 10 meters per second squared. Okay, and it's acting downwards, so I'll give it a minus sign, and then I'll say j hat to indicate that it's going down. But the magnitude of this force is 2 times 10 is 20 newtons. And it's newtons because we're using SI units, mass in kilograms, and meters per second squared. So that says minus 2 times 10 j hat newtons. Alright, so let's redraw the vectors involved. So this force right here is the force that the block is acting in the direction parallel to the edge, to the incline there. Okay, now perpendicular to that, I have another vector here that adds up to this one. So here we've got minus 20 j hat. Alright, now what we need to do is work out what is this angle down here. So we see we must have 60 degrees there. So this is 60 degrees there. And this down here has to be 30 degrees. Okay, now I'm going to call this one equal to B. We've already called it FG, but I'm going to rename it B now. And then I have, say, another vector A equal to root 3, 1, right, that we worked out over here. It's not necessarily this one, but we know it has the same direction as the vector we're after. Okay, so you can see that the projection formula of B onto A is quite relevant here. It will give us this vector, right? The vector that we're after. So let's use the projection formula. So the projection of B onto A is equal to A dot B over the norm of A squared times the vector A. Okay, now let's rewrite this one as a column. So we've got 0 minus 20. And then let's actually just calculate the dot product here. So we've got A is root 3, 1, and we're dotting that with 0 minus 20, dividing by the norm of A, which is the square root, or the norm of A squared. Okay, so inside there we've got the square root of root 3 squared plus 1 squared, and then multiplied by the vector A. Okay, let's simplify that. So root 3 times 0 is 0. 1 times minus 20 is minus 20. The norm of this vector is the square root of 3 plus 1. So the square root of 4, which is 2, but we already know that from there. So this will be 2 squared, and then root 3, 1 is our vector. Okay, so simplifying this, we've got minus 20 over 4, which is minus 5, root 3, 1. Okay, and now if you look at this and take the magnitude, so this is the projection of B onto A, which is the vector right here, right, that we're after. So if I'm to determine the magnitude of force required so that I could push against this and keep that in equilibrium, I have to oppose that. So to oppose, apply the opposite force, which would be 5 root 3, 5. Okay, but we want the magnitude of this. So the magnitude of that vector is the square root of 5 root 3 squared plus 5 squared. So that's 25 times 3 is 75. 25. They add up to 100, so the square root of 100 is 10 newtons. So I would have to apply 10 newtons there. Okay, so I hope that helps in your understanding of the applications of some of these things that you're learning. Alright, so next I'll move on to talk about the week 6 material.